the last thing we began discussing was message switching. And I asked you to compare circuit switching and message switching. And so far, we only noticed that message switching requires more complexity, because now you have to divide the whole conversation into smaller pieces, and those pieces have to be, every time you send a piece, you have to choose a new path. That's one thing. And you have to glue them back together, so you need some glue on the other end, which is more work. But what are the advantages of message switching? Why do we need all that extra work if it doesn't give us any benefits? What do you think? You don't think, or you don't know? Well, you should think. Make an educated guess. Why? Is there a reason to have more complexity? Maybe they invented it specifically to make students' lives harder, such that during an exam, I can ask questions about message switching. Nobody really uses it, but you have to remember about gluing them together, breaking the whole thing into pieces. So that would be a purpose.
On a message, yeah, we split them in smaller. When it gets, if it is smaller, it's not faster. And then
well,
we send it. So
that would be a benefit.
Yeah.
It makes sense, and let me give you an example. Let's say that at the transport layer, instead of a person who has a boat, we use a person who really knows how to carry bags. And that person has to transport a library of books. You cannot load the whole library into the hands of that person. You have to break it down into smaller pieces. And that person can carry 20 kilograms in each hand. So you take this whole data set, you break it down into pieces which weigh 20 kilograms each. You give them to the carrier, off they go, and then they do the same. And you keep repeating that until the whole library is on the other end. And then it's somebody else's job to put those bags together into another library. So my example actually illustrates another thing, that sometimes you have some physical limitations in your channel. So you can't send everything at once, but if you break it down into smaller pieces, then it becomes manageable. When it comes to speed of delivery, I can use the same analogy. So if you have to carry 20 kilograms in each hand, you move like this. But if you only have 5 bytes here and 5 bytes there, then you can do, you can fly like a butterfly, and you move faster. So yes, your answer makes sense. It can make communication faster in certain conditions. Anything else?
Maybe message switching doesn't hold the line.
That's another good example. So, do you know the joke about, so there is this public payphone, and there is a person inside talking on the phone, and there is a queue of 10 people waiting for them. And this person stands like this for about 20 minutes and doesn't say anything. And people here begin to knock at the door and tell him, get out if you're not using the phone. And he says, hold on, I'm talking to my wife. So the thing is that in circuit switching, the whole circuit is busy while these two are talking. And if one of them happens to be in this conversation, then others cannot use the same path. However, if you break down the bigger message into smaller chunks, then you send one chunk first, once it's sent, somebody else can use the same path for other purposes. So this sort of makes it possible for others to use the same resources while you are not using them. Because when you talk to someone, you could skip every few milliseconds of that experience and let somebody else use the path throughout that time. So basically, with message switching, you can share this with other players on the field so they could take advantage of the existing infrastructure. So it makes sense. There is one more thing known as packet switching. And the idea is that every message is split into smaller chunks known as packets, and every packet takes a different path. So one packet goes this way, another one goes this way, another one could go that way, etc. So the difference between this and message switching is that you further break it down into smaller pieces. So packet 1, packet 2, packet 3, and so on. And it's time for more analogies to illustrate it better. Imagine that what we are looking at is the transportation grid in one city. And this is Stefan Chalmari, our main street downtown. If we were in circuit switching, then if there is one car going on the street, no other car can be there at the same time because the whole circuit is busy. And that would be terribly inefficient. The same thing would happen if instead of a car, you would have a bike. I mean, it's still a unit of transport using the whole circuit. So if one bike is on Stefan Chalmari Street, nobody else can be there until the bike reaches the destination, so the whole resource is available for others to use.
Or wagons.
Huh?
Wagons.
Wagons. What about the wagons?
Well, it is more reliable with the one wagon at a time on the path.
You mean like a railway station?
Yeah.
Because in that case, you have to be the only one. Mm-hmm. Message switching, on the other hand, allows you to do something else. So let's say we allow more than one car to take the same path. So all the cars choose to go this way. So you see how thick this line is because everybody is using it. So this street is completely saturated with cars. There is no room for a pedestrian to make a step because there are cars everywhere, just like in our neighborhoods when you want to go home. While the rest of the city, like this part, is not very used. So this has some problems. First of all, as people who maintain this infrastructure, we have to pay taxes for these roads to exist. We have to paint markings on them. We have traffic lights, traffic signs. So we make it all available, but nobody is using these streets. So that's a waste of resources. So in that case, it would be very useful if we could somehow divert some of the cars from this path and tell them, you know what, take this way instead. Maybe, well, not maybe. but it will definitely make life better for everyone, because these people, even though they are on the main street, but when the whole thing is filled, super saturated with cars, nobody moves. Or they move at a speed of 1 meter per minute, which is not very fast. So in a network, we have to somehow find a way to evenly distribute the load such that all the paths are equally loaded. This way we get more happy people. Is this making sense? Let's get back to packet switching. Packet switching is operating with much smaller units, known as packets. And every packet will take a different path. And this, again, has some side effects. For example, let's say that you already notice that some paths are longer, while some have a smaller length. And if one packet went this way and another one went this way, so let's imagine this. Packet 1 went this way, and packet 2 went this way. Physically, if we look at the timeline, so this is time plus plus. This is when we sent packet 1, and this is when we sent packet 2. But because this distance is smaller than this one, then packet 2 will arrive sooner than packet 1. So in the case of circuit switching, things were very simple. The order in which I receive messages is the natural order in which they were sent. But in packet switching, you could have some interesting side effects, such as they are sent in this sequence, but you receive them in this sequence. So this implies that whoever receives all those packets needs to apply some additional effort to reorganize them in the proper sequence that they should be in. That's one thing. The second thing is that sometimes you can have duplicate packets. For example, let's say we send it through this path. This one, A, B, C, D, E. This was node E. So the packet got from A to E. E sent it to the destination, but the destination did not send back a confirmation that they actually received it. So E, after a few moments, says, D appears to be offline, let me send it this way. So it sends the packet again through this node. And this one forwards it, it gets there, but at some point, the message that was sent this way was actually delivered. It was only the acknowledgement that did not arrive back. So now this node, which again is D, this one is C. So now this node has two copies of the same packet. One of them came from this direction, and another one came from this direction. So you have duplicate packets. How do you know what to do about it? For that, you need to have some identifiers on each packet. For example, this packet has ID ABC123. And that packet has the ID ABDEF65. So they are different. But if they have the same ID, then you know that they are duplicates and you can easily discard one of them. Видеокамера. Смотри, at dupes or duplicates, then another problem you had is reordering. And another problem that may occur is that some packets are just lost. So when the recipient has a bunch of packets, it's going to try to reassemble them. So they will prepare some buffer where everything is stored. So they say, I have packet 1, 2, 3. I don't have packet 4, but I have packet 5 and 6. So now they could somehow communicate back to the sender saying, I got everything except packet number 4. Please resend it. So they have to resend only one small piece of data, this one, the one that was missing. But if we use message switching, then even though, well, in the case of message switching, you would have to resend the entire message, which has a bigger size than just this small packet. So packets can be lost, but you can request it to be resent, and you only send again one small piece rather than the whole thing. Another thing is that you can have loops. In network, you have all these nodes which forward packets to each other. And when this node sends something to D, it doesn't really know which path it will take. Is it going to be this one or some other one? It only knows that I have to ensure that this packet is delivered to my neighbor, and then it will be the neighbor's problem to figure out which path to choose. And depending on different circumstances, such as how saturated this segment is versus this one, it may go this way or that way. So remember that in a packet switched network, you are usually concerned only with sending the PDU to your neighbor, and then it's somebody else's problem to take care of it. So the same thing happens here. It only sends it to this node or to this one, and then it's this node's problem to get it to the destination. So it could be so that it got forwarded here, this node chose to send it over through C. C tries to connect to D, but this thing happens to be offline. So it says, well, what can I do? I'm going to send it to this one and make them think about it. This node will face the same challenge, and it might make the choice to go this way. And when this one gets it, it may decide to send it to C. So you can make a loop, and unless there is some mechanism to prevent you from infinitely bouncing the message from one node to another, it will indefinitely live on the network. So you will be occupying this resource for no good reason. So you could have loops in such cases. Therefore, in a packet-switched network, you have to have some protocol that takes care of those loops. And to give you a preview of what is about to come in some other week, in some protocols, there is a field in their header called TTL, time to leave, which is a number that is decremented every time the message, the packet goes from one node to another. So when I send it originally, I set the time to leave to 5. When it gets to the next node, before forwarding it, it applies some changes. One of them is to set the TTL to 4. and then to 3, and then 2, etc. So this way, even if there is a loop, it will not be an infinite loop. Because when TTL reaches 0, the packet is just discarded. It's not forwarded any longer.
So destroyed?
Huh?
Package will be destroyed?
Yeah, discarded, lost, tossed into the bin, thrown away, dematerialized, etc. Yeah?
Yeah, but at the same time, we have to ensure that TTL is
long enough for it to
enough
actually
to
get
reach
there. Yeah, so that protocol needs to take care of this aspect of the problem as well.
Yeah, and you have to know how many nodes are till the end of till the receiver.
Yeah. And to illustrate switching in another example, when you go to a store, you have to choose. So once you have all your products, so you made your groceries, and then you have to pay for the stuff. And you have several lines to choose from, with a person who scans the products, takes your money, gives you the check, and get the hell out of here. So you have one line, another line, and another line. So some of them can be longer, others can be shorter. So you have this, the first thing is a psychological problem. You think, so you are right here, and you're asking yourself, which of these lines should I take? This one is shorter, maybe I should go there, because none of us wants to waste time in the store, right? But this line, even though it's a little bit longer, it moves faster.
Express line.
Or maybe there is even another one which is shorter, but somewhere in this line there is one person who is really, really slow, and they have a lot of stuff. So even though this thing looks promising, there will be a major bottleneck somewhere in this queue. So you have to make a choice. Now once you've made your choice, let's say this one, you are committed to this choice. So it's just like in circuit switching. Once you made the choice, you have to stick to it. You cannot change your mind. So you chose this line, you will be served by this person, not anyone else. So this is one example. But if you observe the world around you, you might notice that some stores or some institutions use a different queue, where you have multiple servers, but you only have one line. Whenever this server is available, the person first in, first out, you go to this one. If this one is available, the next person goes to that one. So what is the difference between this scenario and that one? Which of them is faster, in your opinion?
Second.
Why?
At least it creates the feeling about it's faster.
I think it's actually faster because you're not switching between, you're not running between two different lines, but it's almost like you are, because wherever it's free, that's where you go.
You don't have to think about which one is better. You just go for the one that it's free.
And you may observe that sometimes this is the case. When you have a long, let's say a corridor with servers, you are on this end, and you don't even see this far on this edge. And you chose this queue, whereas in fact somewhere on the other side there is one server that doesn't do anything. And usually there is someone in the store who says, example, you have a fair distribution. Every server is loaded, and that's good. So you could say that this is sort of like a packet switched queue, because whenever one resource is available, someone uses it. You don't stick to one choice and then, while the rest of the network is not busy, someone is working in zombie mode. Yeah?
And the second example is not always faster because, for example, we have on 4 servers, we have 4 clients which have a lot of products. And people who have, for example, 2 products are waiting. But in the first example, choose this randomly.
Sometimes you're lucky, and sometimes you're not.
Yes, it's not always fast.
But it depends on which one you're looking for. For the server side, it's always faster than the second one. But for the individual client,
well, which is why some stores have another line that they call 10 items or less, or X items or less, where you can go if you know you don't have a lot of stuff to process. So the summary so far about packet switching is that it allows us to use the network resources more efficiently at the expense of more complexity. And let me give you another example. As a programmer, you would probably have to think about implementation details. How would you implement some software here that has to be able to handle packets? In the case of circuit switching, you just receive the data, you process it, and that's it. In the case of packet switching, you have to have some buffers where you keep those packets, and when, after a while, when you have sufficiently many packets, you can try to reassemble them, reorder them. And then you have to look for duplicates. How do you do that? You have to remember their identifiers. You need to have some data structure where you keep packets, their IDs, and their contents, and at regular time intervals, you process the data structure using some algorithm which takes CPU cycles, megabytes of RAM, some swap memory on the hard drive. So it's more complexity, more code to write, more logic to debug. Keep that in mind. We can also see networks using another criteria, which is topology. And this refers to what it looks like logically. For example, one type of topology is the bus network, where you have nodes connected like this, A, B, C. If you want to talk to C, you have to do it through B. And if you want to talk to A, you have to do it through B. It can go this way, and it could go this way. So they are connected in a straight line. What are the benefits of such a topology? What do you think?
Little wires.
So you don't have to have a lot of wires around. It means less holes to dig, less holes to drill through walls, which is a good thing.
One single channel, you know that you have just one channel and you go through it.
What are the disadvantages?
One single channel.
There won't be loops.
Okay, there will not be loops. Is it a disadvantage or an advantage? But what happens when someone cuts this line? Or Union Fenosa does interrupts the power supply and what happens then? Huh?
Use your bike.
So in that case, instead of having one big network, you have two smaller networks. So there is some reliability sacrifice that occurs. It's less expensive, as you pointed out. It's easier to construct. But then if there is an outage in any segment, then the whole network becomes, well, it breaks apart.
You can easily find out which network breaks apart.
Yeah, and you have to send some people there to switch the power supply again or reconnect something. It requires effort. So there is another topology known as the ring topology, which is basically the same thing, but there is a link between the last and the first node. So I could draw it nicer like this. And if this link breaks, you can still have a perfectly functioning network, because you can go the other way. Someone's cooler is making so much noise that I can hear it from here.
Yeah.
Well, you should disassemble the machine, take the dust out, close all the windows, open them back, and it should work better. What are the drawbacks of a ring network topology? Distance? What do you mean, distance? Well, in this case, because I drew it as a line, you have the impression that this is a really long connection. But in this case, it's not that of a big deal.
You can still have two cuts, and you'll have two networks.
Okay, so now if we have two problems, we're back to the same result. So this network, this topology is adding some redundancy. Redundant means more than necessary. So we added this extra link. So we paid the price of another cable, and we got some more reliability in turn. So redundancy, reliability. You have more of this, and you have more of that. You have less of this, and you have less of that. Another topology is the mesh network, which is what we had here. It's not a bus, it's not a ring, it's a little bit of everything. So that's a mesh network. What are the benefits of a mesh network? Reliability. Why?
Alternative paths.
Mm-hmm.
More than
So, for example, if this link breaks, this node can get to that one this way, that way, or this way. So there is even more redundancy. Mm-hmm. And that's an advantage. And the disadvantage, naturally, is that you have more wires, more bills to pay, more infrastructure to maintain. There is also such a thing as a full mesh. Which is basically if you have, yeah. In this case, we have some sporadic connections, but a full mesh implies that there is a connection between every node to every other node. So there is a lot of redundancy here, but there's also a lot of reliability. If there is some nuclear blast here, the network is still able to function perfectly.
Also the distance between nodes.
Huh?
Distance between nodes, it's also short.
Well, the topology doesn't necessarily tell us anything about distances. You could have the same thing, but spread it all over the planet.
It's direct connection.
Oh, so you mean, yeah, the number of hops. The logical distance between each of them is 1. Whereas in this case, for example, the distance can be as great as 1, 2, 3, 4. But if it's a ring topology, then it's a little bit smaller. Another one is star, which looks like this. You have some central node, and everybody is linked to that node. Is it better than a mesh network? And if so, why?
It depends on the central node, so if it is off, you don't have any communication.
Yeah, if it's off, you have 1, 2, 3, 4, 5, 6 little networks made of one node each. Yeah.
So actually, this is what we use at home when we have a router, 3 computers, and all the computers are connected to the router.
To one box?
Yeah.
So yeah, this topology is common practice in a household. Of course, this node, if it fails, there is nothing. But then you could also have it, you could have a computer that has, well, not necessarily a computer, but this device. You could have 3 different power sources. It could have multiple redundant connections, so you make it more resilient. And no party is complete unless I add this word here. You could have a little bit of everything. And in fact, this is how the world works. For example, if this is the Ministry of Defense, they have a full mesh because, nuclear blasts, business as usual. But then you can connect them to the rest of the city using, or the rest of the networks. You can use a bus, which could be a backbone that goes through, it starts at somewhere in Portugal, and it ends somewhere on this end in Vladivostok, if we were looking at our planet. So you have this backbone, which is a bus, and somewhere here, let's say this is Chisinau. This node, if you zoom into it, it could be a star or a ring, etc. So you can bind them as a function of your needs. And you always have to consider the trade-offs. It's either very reliable but very expensive, or less expensive but not very reliable, or it might be cheap and very fast but not reliable, or it could be very reliable but extremely slow. So you have to consider the circumstances and make your choices based on that. What are your questions about topologies? If you have no questions, let me generate a couple of them.
I have one question.
Yeah.
How the connection and the routing is handled in different
Topologies.
topologies? Yeah.
Well, you have protocols designed specifically for that thing. For example, So you ask specifically about routing or about who gets to talk in a...
Well, for example, we have a bus topology, and I want to send a message from one end to another end. How do I talk to my neighbors?
So what do you tell your neighbor?
Yeah.
First of all, you have to control who has access to the physical channel. And an example I can bring up is a concept known as the token ring. So in a ring topology, there is some, let's call it, well, it's a token, it's something that every node has in their possession for a small period of time. So for example, the token is currently here. It means that this node can talk. So they send a message. Once they finish their transmission, they transmit this token to the next node. And now it is the one who gets to do the talking. Once it sent its message, it's transmitted to the next one, and so on. So you don't talk whenever you feel like you want something to send. You only talk when this thing reaches you, because then you know everybody is listening. And in this case, the protocol has to take care of several things. What if this node will keep the token for an hour? Does it mean that everybody else is going to stay silent and be unable to say anything? Or what if, while this token is transmitted, something happens and it doesn't arrive there? So now everybody is waiting for the token to arrive, but the token vanished in the ether. So what is going to happen to this network? Is it going to fall silent forever? Or is there maybe some supervision node that has a very precise timer which counts how long it takes for the token to make a full circle? And if it hasn't arrived back within, let's say, 5 seconds, it will re-instantiate another token and again begin to pass it to the next person in line. So the answer to your question is it depends on the protocol and on the technology. There are other criteria as well. For example, the communication mode. One example you've been exposed to already is broadcast, which is what is happening right now. Whenever I say something, all of you hear it at once, simultaneously. An example of such communication is radio or a broadcasted TV signal. Whenever let's say there is a tower that transmits it, and everybody receives it at once. But there are other ones too. For example, unicast, which is, let's draw something here. If this is the sender is sending something specifically to this node. Uni, single, one. Broadcast is when you send it once and it arrives to everybody at the same time. There's also multicast. When you could have, let's say, a subset of nodes to which you can talk at once. So when I multicast to this group, then only these two nodes get the message, while this one or any other ones are out of the loop, so to say. So that's multicast. And there is also such a thing as anycast, where you consider your mission complete whenever one node receives the message. It doesn't matter which one, but when it arrives, that's it. Where would you need an anycast form of communication? What do you think? You don't know yet. But if you think about it, then you might have an answer. Don't give me an automatic, I don't know.
For example, if you're let's say not dying, but you feel very bad. And you want to tell at least one man to call the ambulance, like you cannot.
It's not a broadcast.
Any kind. Yes, anybody.
It's not a broadcast.
No, you can.
You're like a tower.
You're satisfied.
Send a message.
Let me finish the idea. Yes, you are satisfied when at least one person sees you
And acknowledges.
and you can silently pass out. Because you cannot hold on.
Okay, let's see, Svetlana.
SOS.
SOS.
Yes.
Well, it's the same time.
Why is it not broadcast? Because you're sending it to...
Let's define a tower, like for like national television, yeah?
Mm-hmm.
If nobody is connected, nobody have their TV turned on, it's some person, it's a broadcast or anycast?
It's a broadcast because the signal is still physically everywhere.
And when you shout, for example, SOS,
Mm-hmm.
you're like
It's the same thing.
It's a broadcast?
I would say so, yeah. Because,
You're like spreading physically the message.
yeah, physically it's all over the place.
Even if you shout or it's a radio silence, you're good.
Well, it's something for you to think of on your way home.
For example, if you want only two persons to receive the message, for example, you have two persons who are connected to your television,
Mm-hmm.
and third person who are connected to but didn't pay for this month.
Mm-hmm.
So, for example, you don't have to give internet, for example, for the third person who didn't pay.
Yeah, but how would you control that? You would have to know specifically who is connected to you, so you know who gets the service and who doesn't.
I don't know, that's the technology of the Nexus or another network of this.
Mm-hmm. You had something to add?
Yeah, or for example, if you prepare a test for us, it
Mhm.
doesn't matter whom you tell that we'll have a test, you'll be sure that anybody will know that we'll have a test and prepare to it.
Mm-hmm.
So it's an anycast, you don't care how the message will be spread between us in a
Spread.
group.
Mhm.
But you can tell to anybody and the message will be received.
Eventually propagate.
Yeah.
Mm-hmm.
My job is done here.
Yeah. I also have to tell you one thing that you may not be aware of it, but in many networks, everybody gets to hear everything. even if it's not for them. And whenever you receive a message, you look in its header, and it might have a field such as destination ID or destination address. So everybody receives the message, they open up the header, they see what the field destination address is, they compare it to their own address. If they match, then they know, aha, this is a message for me. If they don't, they just discard the message because it's not for them. But physically, everybody gets it. So, for example, in this class right now, I could say, you know, when they sing a song, at some point you say, just the boys or just the girls. So I could say, just the girls in this class. What time is it? And everybody physically receives the message, but the boys will see, well, am I a girl? And they will probably say no, so they will ignore the message. And of course, vice versa. So we will discuss this in more details later, but this completes the answer to the question that you asked previously. What do you usually place in the fields? Destination address is also something you keep in the header. And when you look at things from a perspective of security, you realize that all of your communications are actually physically on the entire network, and someone, if they really want to, they can write software that will not discard the message if they have a different address. They can still read it. So this depends on many things, and we will eventually talk about them. You could also consider networks and classify them by size. For example, there is such a thing as a pen. Do you know what it is? Is it the object you use to make pancakes or to fry fish? Or is it a personal area network? For example, Bluetooth is what people usually use to make a personal area network. This microphone is attached to some device right there. It's very, very small scale. Typically, you use it for devices that are on the same person. For example, your headset, such as this one, you see it has no wires. So I put it this way, and it's connected to my phone. And it works from this far to wherever my phone is, here or maybe here or in the bag. A few meters, the range, it works. Of course, you cannot use this technology to connect Chisinau with belts because it's too far away. But on a personal scale, that's the right thing. You also have such a thing as a LAN, a local area network, which is slightly bigger. And this slightly can be quite big. For example, when I was a student, about your age, I guess, my classmate and I, who lived, at a certain distance from each other, we were very huge fans of a game called Worms. And we played it when we were together, every time. And we wanted to extend this experience and be able to play it anytime we want, not only when we are physically together. So we thought it's time to build a network between our houses. And if anyone here is from Buyukan, you know the street Alba Iulia. So he was on Alba Iulia 186, I think, and I was in 200/1. So you have quite a few blocks to cover. So we thought that it still needs to be done, so we began talking to the people in our neighborhoods and encouraging them to participate in a network project so that we would link them to the network, and the network would also grow this way, and at some point there would be a link, and myself and him would be able to play Worms without getting out of the house. We never completed this project, but the network began to grow from this side, and if you are from this area, you know the last building, at least at that time, was Albeit at 206. And we covered this distance, and it went a little bit this way. But this is where we had a problem, Strada Liviu Dileanu. We had no knowledge on how to take over this natural barrier.
Underground.
Well, we didn't have shovels that would be able to do it that way. So a local area network could be something that fits in this room if we hook them together. It could be also a network that has this room and that one in one place, so it still qualifies as a local area network. And in this case, because of the distances, so they were linked logically in one LAN. But in this case, we couldn't cover this gap anyway. So hypothetically, you could say we have a local area network here and a local area network there, but between them, there is no link. But there is also such a thing as a MAN, which is a metropolitan area network, which takes it one level up, which could be treated as an interconnection of such smaller networks. And there is also a term WAN, wide area network, which is even bigger than this. You could have multiple cities. Yeah, so you could say that the internet is a very wide area network, or you could call it, let's say, planetary area network. Though it's not accurate because there are satellites in orbit which are also connected to this network.
Also on Mars.
So you can make those connections and it still works. So it's not planetary any longer. So based on size, you have those. And you can also use other criteria, such as by purpose. You could have a business network, an academic network. You could have a gaming network, medical network, etc.
When the internet was slow, this kind of local area networks were very popular. Like where people share data between them and play games.
Yeah, that's exactly what we were doing here. One of the people who lived somewhere here had an ADSL modem, which was much better than having a dial-up modem, which would use the phone line. And when you are connected to the internet, someone, if they pick up the phone, they hear as if someone's sending a fax. And it's really slow, it's expensive, it's not fast, and no one can use the phone while you are on it. So we wanted to build our own LAN so that we could share that internet connection, and it worked. It was an interesting project. All of us learned a few things about networks. And one of your future assignments in the labs will be the reverse engineering of a chat program that we were using here to talk. But that's for later. I will explain why this is an interesting challenge, how to do it, and why it makes a difference. Up to this point, what questions do you have? Ask them now.
Getting laboratory works.
Go ahead.
How exactly we submit them? Like the contents of the report?
Yeah, so you have to send me an email where you have at least a couple of attachments. One of them is the report, and the other one is your code. You can put it in a zip archive, you can put it in a 7-zip archive. I will figure out what to do with it. Don't send me compiled programs, send me the code. And yeah, I guess that's it.
The report, what should it contain? Like the discussion on the code, comments?
Mm-hmm. So I will try to answer this question in the following way. Imagine that one of your colleagues was absent in class, and they have to do that assignment. And you want to help them. So in your report, you have to contain that minimal subset of info that is necessary for a person who has absolutely no clue about what's going on to understand what is going on and be able to replicate the experience. So, and it's up to you to decide what is that minimum necessary. So you might choose to explain every line of code. You might choose to just tell me which functions you wrote and how you use them. Or you could draw a flow chart or a sequence diagram. It's up to you. Different people express their thoughts different ways.
Can we just use GitHub repos?
And send me the link to that thing. Yeah. It works as well. Another thing is that if you have an assignment which sort of works but is not really complete, you can send it to me for a review. I could provide some tips. You can update it and then resubmit it. So there is absolutely no limit on the number of times you can send it to me. I give you feedback, you use that feedback to make it better, and then you send it again. It's not going to have a negative impact on your grade. So actually, it's a thing you should take advantage of. The more often you send me questions and beta versions, the more feedback you get, so the better you make the program by the time the deadline expires. So up to this point, I only received one question from you back then, when you had the thing with threads. So either it means that nobody else has questions, or people do have questions, but they are worried what I will think of them when I hear the question. Don't worry about that. So go ahead and ask.